Hi, so we are at module 27. In this module, I am going to talk about sequential circuits, and I will also introduce the notion of what is called a state machine. So, we are going to look at synchronous sequential circuits. A synchronous sequential circuit is one in which you have flip flops and you have combinational logic. So, you have a combination of both of these, and the combinational logic has its set of inputs, and you have a set of flip flops. So, as a circuit, what you have is you have a set of what are called primary inputs. So, the primary inputs are, so if you think of a chip as a black box, those are the inputs that go into the chip. So, we will call them the primary inputs, and there is a set of outputs that is coming out of the chip, we will call them the primary outputs. So, any module or block or chip that we design has inputs and outputs, and we have a set of flip flops, and we are going to call something a state. So, a state of a system or a module or a block is defined as the set of values that the flip flops have at a particular point of time. So, of course, when we have many flip flops, we also have to name the flip flops. So, we will assume that there is some implicit naming of the flip flops or numbering of the flip flops, and once we have that, each of the flip flops can take 0 or 1 as a value. So, if I go and inspect the circuit at any point of time, I go and see what the values for various flip flops are, and I can report that this is at a state which is given by the vector of the values that the flip flops take. So, clearly if I have n flip flops, then I will have 2 power n possible states that the flip flops can be in. So, I can say that the system can be in 2 power n states then. So, let us look at a basic sequential circuit. So, I am going to call this the canonical sequential circuit, because this is the most complete form of a sequential circuit. So, in a canonical sequential circuit, what you have is you have a set of flip flops which are called the state register. So, we have a state register. So, even though it is shown as one single box here, in reality it could be any number of flip flops. Let us assume that there are some number of flip flops here, and it is a register, which means it takes in a value and you can also tap it out in parallel. So, you can give inputs in parallel to all the flip flops, and you can also tap out the values in parallel from all the flip flops. So, you can go back and look at parallel in parallel out register, just in case you want to refresh what the state register is. So, it is just a basic register, it is a collection of flip flops, each one can take one input and it can give one output. The collection of these flip flops can all be accessed in one cycle. So, you have a bunch of flip flops together, and we have two forms of combinational circuits. One circuit called the input forming logic, which is shown here, and one circuit called the output forming logic, which is shown here. So, what the input forming logic does is, it takes the primary inputs and it takes the values from the state register. So, the output of the state register and the current set of inputs, you take them and then it is sent through this input forming logic, or sometimes it is also called the next state logic. You have that, and you also have the output forming logic, in which the state register along with some signals from the input forming logic form the output forming logic. So, let us see this circuit in its in all the glory that it has. So, you have a state register, the state register's inputs we are going to call it the next state, and the outputs we are going to call it the current state. So, at any point of time, right. So, you have the current state, and the current state goes through the input forming logic. This is a combinational circuit, they will come and appear as next state. However, this next state will get registered, will go into the state register only when the clock comes in. So, I am going to start from the point where the clock has already come in and there are stable values in a register. We will call that the state of a system, and once I have state of the system, I take the current state and the set of inputs. With the set of inputs and the current state, I can get what is called the next state, and the next state will come and be at the inputs of the state register. Until the next clock comes in, the values in the next state will not be copied to the current state. Remember, this one is a bus, it is not a single line, it is a bus, and similarly it is a collection of wires here. So, all these thick lines are actually multiple wires, and each flip flop is supposed to take its corresponding input and place it at the output. And you also have this circuit where you have the current state and the output forming logic which gives the outputs. So, the meaning of this line is that the inputs are also passed on to the output forming logic. So, this arrow and this line here means inputs are passed both to the input forming logic as well as to the output forming logic, and from there you get the outputs. So, this is the canonical sequential circuit. So, we will talk about various variations of these canonical circuits later, but as of now just remember that there is something called a state register which has n flip flops, there are 2 combinational blobs, the outputs come both from the input and the current state, and the next state is derived from the current state and the inputs, and such a machine model is called a Mealy machine model. So, it is named after a person, it is called a Mealy model. There is a small variation of this model which is called the Moore model. In the Moore model, what happens is you have the same input, you have input forming logic, state register and output forming logic. However, the connection from the inputs to the output forming logic is missing. So, in the Moore model, outputs of a circuit are a function of the current state only, it is not a function of the inputs. So, unlike the Mealy model which I have shown below, so I am showing it as a grayed out module. So, this is a Mealy model in the bottom. The Mealy model, if you notice, the inputs are going to the output, which means if I look at it from the primary outputs perspective, both the current inputs and the current state can control the outputs. However, in the Moore model, the primary outputs are controlled only by the current state. So, the current state dictates what the outputs are, it is not dependent on the current inputs. So, current inputs can only influence the state, and state in turn has to influence the output. There is no direct influence of inputs on the primary outputs. So, such a model is called the Moore model. So, these are 2 different models. We have already seen a few circuits, and some of these circuits actually fall under one or the other model. We can come back and look at that later. So, the first aspect of this video is going to be about analysis of sequential circuits. So, given a circuit, it is usually useful to find out what the circuit is doing, and this is a fundamental requirement from digital designers, and it is also a good skill to have, given a circuit what it does, rather than asking you to design a circuit to solve a particular problem. This is the other way around, we are analyzing what a circuit is doing. So, usually this analysis goes in 3 steps. The first step is you write a bunch of logic equations which determine the flip flop excitation and the sequential circuit. Basically what it means is, if you are given a circuit with flip flops in it, you have to first of all find out what the flip flops are. You should know the excitation table of the flip flops. If it is a D flip flop, you should know what it does, if it is a T flip flop, you should know what it does, and so on. And you should go and write the output logic equations using the flip flops excitation. So, when we will see a detailed example in the next slide itself, but you need to know the table of equations for the flip flop. You should also be able to find out combinationally what the next set of values are going to be. We will come to that in more detail later. Then there is something called a state table. So, state table is just a representation of the behavior of the circuit. So, remember the canonical model, you are given an input and the current state of the system is stored in the registers. So, based on the current state and the inputs that come in, you will have the next state which is affected. So, a state table is essentially a representation of given current state and given the current inputs, what is the output going to be, and this current state could be any of the possible states. So, there are several valid states that a state register can be in. So, for each of these state combinations and for each of the input values, you have to specify what the next state is going to be. So, the combination of what are the current inputs and current state to what are the outputs and the next state, this is called a state table. So again we will see a example in the next slide. And finally there is something called a state diagram. So state diagram is a pictorial representation of what the circuit is doing. So this is useful for analysis because instead of looking at what the flip flops are or what the combinational logic is and so on, we can go and look at it as pure input output combinations. We can just look at it as these are the inputs and these are the outputs if we have a state diagram. So the state diagram has a few notations. Usually what you have is you have all the states are represented by circles and you put a name inside them. So typically we name them S underscore a number. So you have a circle which represents a state. So if I take n flip flops, it can be in a state. So all the flip flops could have 0 or all the flip flops could have 1 or anything in between, right. So it's possible that your set of flip flops has 2 power n states. So the states could be numbered S0, S1, S2 and so on up to S 2 power n minus 1. So let us assume that there is some state j, Sj, and we are going to have this notation that this state Sj, you have a transition that is coming into it. So what you see here in the bottom is the how you give notation for a state machine. So what you have is all these circles are represented by states. So each state is marked with a number Sj, Sk and so on, and the meaning of this part of the circuit is if the current state is Sj and on getting some input Ik, it will go to the state Sk and produce a output OK. So the current state input combination drives the circuit to state Sk and it should produce OK as the output. So such a model is called the Mealy model, and equivalently there is a Moore model. A Moore model is one in which you have the state Sj, and remember the outputs are completely controlled by the state itself, right. In a Moore model the output depends only on the state. So what you can do is on arriving in the particular state Sj, you can go and you can immediately tell what the different outputs are going to be. So usually you mark it as Sj slash Oj. So Oj is the set of all the outputs at state Sj, and on getting an input Ik, you go to the state Sk. Again, because it is a Moore machine, the state uniquely determines what the output is going to be. So from Sk you can uniquely say what all the outputs are going to be. So this is a graphical representation. This will get clear in a little while once we see the example. So let us take a particular state table and a state diagram. I will give a picture of all these things first and then we will look at an example which takes a circuit and gets you these details. So if you are already given a state machine, for example here is a state machine which has 3 states A, B and C, and I want you to get comfortable with the notion of what the state diagram is and what a state table is. So let us look at this. We will call this a state diagram because it is depicting states. In this example there are 3 states. The states are named A, B and C, and let us look at each of these arcs. So let us look at this arc first. So on this arc you see 0 slash 0. What that means is on getting input 0, you produce an output 0, but you remain in the same state, the state A itself. That is the meaning. So if the current state is A and if the input is 0, the output is 0 and you remain in the same state. That is the meaning of this arc. The meaning of this arc is if the current state is A and if the input is 1, you produce a 0 and you go to state B. So this is the meaning of this arc. So let me pick another arc here. The meaning of this arc is if the current state is C and on 1, so anything before the slash is input. If the current state is C and if the input is 1, you produce the output 0 and you go to state B. Right. So from the notation I can immediately say that this is first of all a Mealy machine, because the state is not dictating what the outputs are, the state transitions are dictating what the outputs are. So when you go from A to B, on input 1 you produce 0, and when you are in A on 0 you produce 0. So it looks like both the transitions from A are resulting in an output 0. However, you go and look at C, C on a 0 gives 1, but C on a 1 gives 0. So being in state C, you cannot uniquely say what the output is going to be until you know the input also. You should know whether the input is 0 or 1. If the input is 0, the output seems to be 1. If the input is 1, the output seems to be 0. So given this, I can say that this is actually a Mealy machine. So this is a state diagram. Let us not worry about what this is doing. So if you are from computer science, you have probably seen what are called finite automata, either deterministic or non-deterministic finite automata. You would have drawn similar pictures. In fact, there is a very deep and equivalent connection between state diagrams that we see here in digital circuits and automata that you might have read in your discrete mathematics course. But if you are not from the CS background, you do not have to panic. So this is just a picture. This picture captures the notion of what are the values of flip-flops and what will be the values of flip-flops in the next cycle, what will be the outputs based on the current inputs. That is all it is capturing. If you want to draw it as a state table, then what you usually do is you go and write the present states. So there are 3 states that are possible, A, B and C. You write them as current states and you write 2 sets of columns, right. So one set of columns called next state and one set of columns for outputs. In this case, there is only one output bit, there is only one input bit. So let us assume that the input is called X and the output is called Z, then the input can take 1 or 0, the output can, so the output is Z. So let us look at the next state first. So let us ignore these columns for now, let us look at these 2 columns for now. Let us see how to fill up these entries. So if the present state is A and if X equals 1, so if the present state is A and if X equals 1, you are going to state B here according to the picture, right. So you put B here. If current state is A and if 0 is the input, you come back to A itself, we mark that here. So let us go and look at C for instance. C on a 0 remains at C itself. So C on a 0 remains at C itself, C on a 1 goes to B, right. So that is these 2 columns. Similarly for the output, the current state and the input will determine the output, right. So A on a 1 gives 0, so A, current state A on input 1 gives a 0, current state 1 on input 0 also produces 0, that is because of this combination. So if you are in A and if the input is 0, you are producing 0 as the output. So that is here. Let us look at C for instance. So C on a 0 gives 1 as output. So C on a 0 gives 1 as output. C on a 1 gives 0 as output. So what these 2 are capturing are the next state comma output combination. The rows are listing the present state and these 2 columns are representing the other combinations which are the inputs. So this is one way of drawing the state table. Another way of drawing the state table is as follows. So you go and put all the input combinations. So the inputs could be 0 or 1. If the input is 0, the present states could be A, B or C. Similarly, when the input is 1, the present states could be A, B or C. This is listing all the combinations. If you look at it, it is looking at all the possible values of X into all the possible values of present state. So there are 2 possible values of X, 3 possible values of present state, there are 6 different rows. For these rows, you then go and mark the next state comma output. So this is another way of drawing the state table. So if you are given a state diagram, you should be able to draw a state table. If there are 2 inputs here, then this input combination instead of 0 and 1, you may have 0, 0, 0, 1, 1, 0 and 1, 1. So in general, if you have n inputs and if you have m states, then you will have 2 power n into m rows. And the number of columns, so in this case again there is only one output. If you have more outputs, you just keep adding columns. So if you have 2 outputs, you put Z1 and Z0 maybe, right. So that is the general way in which you will draw the state table given a state diagram. So we will look at only single input, single output circuits for some time before we go to the other circuits. So, now let us go and do analysis. I am giving you a circuit now. So, this circuit has 2 flip flops and there is some connection here, and I also tell you that these are D flip flops. I am asking you what the circuit is doing, right. If you want to analyze a circuit like this, now we will go through 3 steps. So, I mentioned this in the slide earlier, right. We will go through 3 steps. The first step that we are going to do is we are going to figure out what the flip flop is. What is the flip flop? So, I already mentioned that these are D flip flops. The second thing that, and the second part of the first bullet is we also have to find out what the equations are. So, now let us go and look at the D inputs for each one of them. There are 2 flip flops Q0 and Q1. Let us go and look at the D inputs. If I look at D0, D0 seems to be coming from Q bar of this flip flop. So, I can write D0 as Q0 bar, right. So, if you think about it, these are 2 flip flops. If this is my state register, then this input is coming in here directly. So, Q bar is coming in here directly, which means D0 is Q0 bar. So, it looks like this is part of the next state forming logic. If you take Q0, complement it and give it to D0, that will be your next state logic, right. So, from the current state and the inputs in this circuit, there does not seem to be any input. So, based on the current state, you are able to say what the next state is. So, Q0 bar is D0. Let us go and look at the functionality of D1. So, it takes Q1 and Q0 complement and it, and it then takes Q0 and Q1 complement and it and OR it together. So, it is actually doing Q1 Q0 complement plus Q1 complement not Q0. So, this one is actually the function of XOR between Q1 and Q0. So, D1 is Q1 XOR Q0, and these two are the values for D0 and D1. So, there are no explicit outputs from the circuit, there are no explicit inputs to the circuit, there seems to be a clock and only the flip flops. So, in this case what we have is we have some next state logic and there is no output logic. So, this is why I gave you the canonical picture. So, in the canonical picture you have flip flops, you have combinational logic for the next state logic, and you have combinational logic for the output forming logic. In this case the output forming logic is not there. So, it degenerates the canonical case to something else, but it is still a valid sequential circuit because we still have flip flops in them. Now, let us do the second step. From here, if I want to write the state diagram and state table, so let us first write down the characteristic table of the D flip flop. We have already written that equations. The characteristic table is on rising edge of clock, when D is 0, Q will be 0, and on rising edge of clock if D is 1, Q is 1. We already have that. Now, let us go and write the state table. Right. So, we know that there are no inputs and we know that there are no outputs. So, these two columns can be ignored, but I have given here and I have marked it empty to say that there is nothing to do here. Then I have Q1 and Q0, which are the present states, and I want to see what the flip flop inputs are going to be. They are D1 and D0, right. So, let us ignore this column for a while now. You have D1 and D0. So, based on Q1 and Q0, there are 4 possible combinations of Q1 Q0, right. So, Q1 Q0 is could both be 0, 0, 1, 1, 0 and 1, 1. Let us plug in these values to get the D0 and D1. So, D0 must be Q0 bar. So, if you look at this column, it will be the complement of this column. So, this is 0, 1, 0, 1. So, D0 will be 1, 0, 1, 0, and D1 is Q1 Q0 complement plus Q1 complement not Q0, or the XOR of these two. So, you take the XOR of these two. So, that will give you the vector 0, 1, 1, 0. These two columns seem to be the inputs that are coming into the flip flop, right. So, from Q they went back to the flip flop. So, these are the inputs that are coming into the flip flop. Now, if these are inputs coming into a D flip flop, then the clock comes in, what would happen to the flip flops then? If the inputs had 0 and 1 at D1 and D0. After the clock comes in, Q1 will get 0 and Q0 will get 1, right. So, remember the star notation means next state. So, at t, if D1 is 0 and D0 is 1, at t plus 1 or just after the clock comes in, Q1 will become 0 and Q0 will become 1. So, if you want to get the next state, then at least for the D flip flop case, you copy the D inputs itself directly, those will be the next states. So, 0 1 you copy it directly, 1 0 you copy it, 1 1 you copy it and 0 0 you copy it. Now, what you have is you have present states, you have inputs, you have next states and you have outputs. You do not need the flip flops excitation table, we do not need this one anymore, because this flip flop we got the equations from there, we got the states. So, we do not need these two columns anymore. Now, let us go and look at input comma present state to output comma next state combination. In this example, there are no inputs and there are no outputs. So, there is just a present state to next state transition. So, let us look at the state diagram. If the present state is 0 0, right. So, Q1 Q0 are two different flip flops, and if they take the value 0 0, I am going to mark that using this blue circle and I am going to call this state 0 0, right. I am giving a name to it, state 0 0. So, state 0 0, what happens is if you are in state 0 0 and when you get a clock pulse, you are supposed to go to the next state, and what is the next state you are going to go to? The next state that you are going to go to is on these two columns, you go to 0 1. So, because that is what we have derived so far. So, this 0 1 is the next state. Then let us go and look at 0 1. If 0 1 is the present state, that is this row, we go to 1 0, which is the next state. So, we mark that. And if you are in 1 0 as the present state, we go to 1 1 as the next state, and if you are in 1 1 as the present state, we go to 0 0 as the next state. So, it looks like if we start with state 0 0, in one clock, when the first clock pulse comes, we will go to state 0 1, next clock pulse will go to 1 0, next clock pulse will go to 1 1 and the next clock pulse will go to 0 0. So, I have given the numbers here, you can also name them A, B, C, D if you want. Right. So, this is marking what the values of the flip flops are directly. Many times you just give the names to it, you give the names A, B, C, D and so on. So, the way to read this picture is, if you are in state A, no matter what the input is, in this case there is no input. If you are in state A, in the next clock cycle you will go to B, next clock cycle you will go to C, next clock cycle you go to D, and then you come back to A in the next clock cycle. And this keeps repeating forever, as there are as long as there are clock inputs given to the circuit, this will keep toggling from A to B to C to D back to A, and this will keep going in cycles, right. So, in fact, this is just the state diagram of the up counter that we had. We just designed that in the last class, right. So, this up counter, if I go and read the flip flop values, right. So, if I go and read the flip flops and directly give them as output, then this is actually the state diagram for an up counter. So, up counter should go from 0 0 to 0 1 to 1 0 to 1 1 back to 0 0. So, this is a picture for a up counter. So, I want you to do this as homework. So, we are given 3 flip flops, Q0, Q1 and Q2, and you should always read this vector as Q2, Q1, Q0. So, there are 3 flip flops, the Q2 is the most significant bit and Q0 is the least significant bit, and there is a certain connection given here. The connections are not drawn as wires, but you can see where they are coming from. So, in this case it's Q0 bar is coming here, Q2 bar is coming here and so on. The actual wires are not shown. If this is the case and if there is a common clock input, what I would like you to do is, based on the states in this circuit, again there is no explicit input to the circuit, however there is an output called X which is derived from Q2, Q1 and Q0, and this is the logic description for X. What I want you to do is go and write the state tables for it and draw the state diagram for this. So, in this state diagram you will not have an input at all, you will only have a state transition which marks if you are in a current state, what will be the state that you go to in the next clock cycle, and what will be the output that you will produce. You will not have a input combination. So in the state diagram that I showed earlier, I said current state comma input combination will give output comma next state, right. So in this case there is no input. So let us look at a picture here. What we usually have in a state machine is, if we have state Sj on input Ik, it produces output OK and goes to state K, right. So this is the picture that I showed for a Mealy machine or the canonical machine. For this example, what you would have is something like this. So on state Sj, you will go to Sk producing OK, and the inputs do not matter. There is no input to the circuit explicitly, right. In this picture also you can see that, and this OK is actually just a single bit X. So what I want you to do is draw a table of this form. So let us see what you should be drawing. So I want you to draw a table like this. If the current inputs are Q2, Q1, Q0, and you should figure out how many combinations are there. So this is for the current state. You should tell me what the next state will be, which means you should give me Q2 star, Q1 star, Q0 star, you should give me that, and you should also tell me what X is going to be, right. So you fill up for various combinations here, you tell me what these entries are going to be. Go and write this down. So this is going to be part of your quiz also, it is going to be a quiz question also. So let us move on to a few different kinds of problems. So one of the things that we do with sequential circuits is we can there are two different kinds of state machines. A state machine is essentially you have a set of flip flops, you have the current state, you have the next state, you have inputs and outputs, and such state machines can be used to do two different kinds of things. One, it can actually do what is called detection, right. So let us take a specific problem. I want to detect two consecutive ones, that is the problem description. Let us see the problem description in more detail. So your circuit is supposed to take a single input W, and this input is coming in one bit at a time, right. There is only one bit that is given to you at a time, but there is a series of inputs that is coming in, and this may be a never ending series, and all changes must occur in the positive edge of the clock. I am giving that to you as a constraint, and what I want to do is, when the inputs are coming in, I want to detect if there are two consecutive ones in the circuit, so in the inputs. So the circuit should detect if there are two consecutive ones, output must be 1, output Z must be 1 if for two immediately preceding cycles the input W was 1. Right. So you go and look at the current cycle, you go and look at the previous cycle, if both of them have 1 as the input, then the output should go to 1, otherwise it should remain at 0. So this is the problem description. I will give you a small example here. So let us assume that I have given you something for 11 clock cycles, it could be never ending, so there could be more clock cycles later, and I have given you inputs for 11 clock cycles from T0 to T10. So they are given as W, and we are getting it as 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0 and so on. The output Z is defined as, it should be 1 if the current input is 1 and in the preceding clock cycle the input was 1. So let us go and look at the series here. The current input is 1, but the preceding input is not 1, so the output is 0 here. The current input is 1, the preceding input was not 1, so the output is 0 here. The current input is 1, the preceding input is 1, so the output is 1 here. So wherever you see a 1-1 combination, you will get a 1. This output is also 1 because at T8 the input is 1, at T7 also the input is 1. So the preceding two cycles, so the preceding cycle and this cycle you should have 1, that is the description that we are asking. So this cycle and the preceding cycle we want them to be 1, so we have that here. So in all the other places we have a 0. So let us say this is the problem that we have at hand, and I want you to design a circuit for this. So one way to do this is as follows. So, let us look at the picture here. So, I am in module 27 and slide 10. Right. So, what I am going to do is, first of all the inputs are coming in one bit at a time. So, whenever you see some description like that, immediately what should come to your mind is, this is coming one bit at a time, is there a case for a shift register? So, that is what should come to your mind. So, I am going to see if that is the case. So, let us say that there is a W that is coming in, and if I use a shift register, right, I will have some output, right. So, there is some output going out, there is some output. Now, the first thing I want to see is, there are inputs coming in, I want to find out if the current input and the preceding input are both ones. So, if I want to do that, then if I put it into a 2-bit shift register. So, when the input comes in one clock cycle it comes here, in the next clock cycle it comes here. So, if I want to find out something in 2 consecutive clock cycles, then I can look at a 2-bit shift register. So, W is coming in as input, let me call this R0 and this R1. If I put it into a 2-bit shift register, in this case it is a left shift register, and this will go as R0 and R1, right. So, if I keep giving inputs to it, then so the sequence I gave was 0, 1, 0, 1, 1 and so on, I gave this as the sequence. So, initially 0 will get here, then 0 will move here and 1 will come here, then so let us write it down at so let us assume that at t naught, right, or let us say t minus 1, both of them are initialized to 0, then at t naught I am getting 0 as input. So, what would happen is, this 0 gets shifted here and this 0 gets shifted here. So, you will have 0 0. At t1, if I give 1 as an input, this 1 gets shifted to R0 and this 0 gets shifted here and so on, right. Now, since I used a 2-bit shift register, so let me see how to solve the problem that we have at hand. So, we had W as the input and there was some output that is coming out, that is 1-bit output that is coming out. If I take these 2 bits and I AND it together, what do you get from this? If both of these are 1, then the AND gate will give an output of 1. So, what this is capturing is, if there is any 2 consecutive cycles at which the inputs are both 1, so if there are 2 consecutive cycles where it was 1, if the input was 1, it will eventually appear in the shift register as 2 1s, right. So, at some point if W is 1 1, then at some point R1 and R0 will both become 1. When R1 and R0 are both 1, the AND gate will have an output of 1. This is what we asked in the problem. So, if I call this my output Z, then this circuit is actually capturing the problem at hand. So, the problem at hand was, if there are 2 1s in the inputs consecutively, then the output must be a 1, and this is detecting the case where there are 2 consecutive 1s. So, this is a fairly simple example. Let us make it slightly more complicated. So, in this problem, as before, we have a single input bit W, we want all the changes to occur in the positive edge of the clock. So, we want the shift register essentially to be a positive edge triggered register, and now the output Z must be 1 if for 2 consecutive cycles the input had either 1 in both cycles or 0 in both cycles. So, let us look at this one. So, here you have 1 in 2 consecutive cycles, so the output is 1. At this point you have 2 1s in consecutive cycles, the output is 1. At T8, T7 and T8 are both 1, the output is 1. At T10, both the inputs are 0, the output is 1. Let us say I want to take this problem and solve it, then again it is only a minor extension to what we did earlier. So, again I will draw the picture now. So, we are at slide 11. As before, I will give it to a 2-bit register, and I am now going to give it to a right shift register just for the heck of it. no particular reason, right. So, I will call this R1 and R0, the inputs are coming in from the left side and they are going to the right side, right. So, there is no reason why I should have used a left shift register in the previous one, there is no reason why I should use a right shift register here. So, I am using it arbitrarily. Now, what I want is if the combination is either 0 0 here or 1 1 here, I want the output to be 1, otherwise the output must be 0. So, what I could then do is I can take these two bits if I capture them and if I connect them with a circuit. So, I am going to put a circuit which is going to give my Z. I want to put a circuit in such a way that in 2 consecutive clock cycles, if the inputs are the same, the output should be a 1, right. So, if I want 2 consecutive clock cycles, I tap 2 consecutive positions in the shift register, there are only 2 positions here R1 and R0, and I want to give this combination for 0 0 it should be 1, for 1 1 it should be 1. So, to do that, if I put an XNOR gate, if both the inputs are 0 or if both the inputs are 1, the output will be a 1. For other combinations, if I have a 0 1 here or a 1 0 here, they are not 2 consecutive 1s, they are not 2 consecutive 0s, in those cases the output will be a 0. So, this for this problem, for detecting 2 consecutive 1s or 2 consecutive 0s, this circuit will work. Let me make a slightly another modification to this problem. I want to detect a sequence 0 1 1. So, 0 1 1 is an input sequence. So, I am having again a single bit W and it is getting 1 bit at a time. Whenever there is a 0 1 1, I want to detect it. So, now let us look at this case. So, there is this 0 1 1 here, so the output should be 1 here. Again there is a 0 1 1 here, the output should be 1 here, in all the other places it is 0, right. If you want to do something like this, first thing is you are asked for 3 consecutive cycles. If you want to get 3 consecutive cycles, then the first thing you have to think about is how many flip flops do you want to remember 3 consecutive cycles. So, can you do it with just 1 flip flop or 2 flip flops? So, the answer is no, you cannot remember 3 values, you are asking for 3 values in the consecutive cycles, right. How can you do it with only 1 flip flop or 2 flip flops? You have to remember 3 of them, right. So, as before I am going to use a 3-bit shift register. So, earlier I used a 2-bit shift register, now I am going to use a 3-bit shift register. I assume that the inputs are coming in from the right side and the shift register is giving the output on the left side. So, at some point if I want 0 1 1 to be detected, so the input is coming like this, let us say something like this, and the clock pulse is like this, the clock pulse is something periodic, right. So, you are looking at what the values of input are at different points of clock. So, the inputs are coming in 1 bit at a time, I want to detect if there is an output of 0 1 1. If I want to do that, then I want this to be 0, I want this to be a 1 and this to be a 1. So, I take those combinations, give it to an AND gate. When will this AND gate give a 1? This AND gate will give a 1 only when this bit is 0, this bit is 1 and this bit is 1, right, which means at some point of time the input sequence you should have had 0 followed by a 1 followed by a 1, only in that case the output will become a the AND gate will fire a 1 and this I can drive to my X. So, if I give W as input, then we get Z as output and what we have is a fairly simple circuit in which you get this whole thing running. So, all these are sequential circuits, right. What we have is this is actually this is like the the sequential circuit that I showed earlier, except that there are a few issues here. It is not like a canonical sequential circuit because you are taking in the inputs are fed to the flip flops, which is okay, right. There is some logic connecting one flip flop to the other and so on. The output is a function only of the current states. So, this is actually a Moore machine, right. The current input does not influence the output directly, the current input gets into the register and the register drives the output. So, this is a Moore machine. So, it is slightly degenerate case of the canonical model that I showed earlier. Now we saw 3 different examples. We saw a sequence detection of 1 1, we saw a sequence detection either 0 0 or 1 1, and now we are able to detect 0 1 1. So now you can go and make up your own examples, detect 1 0 1, detect 1 0 1 1 or whatever, and you try and come up with a circuit on your own. So the first thing you will notice is, for a problem like this, it seems to be trivial to come up with designs like this. So I want you to get a handle of such a model, right. So the key thing here is, when we did this, right, there is a certain state of the system, and this certain state of the system is actually changing the way things are working. So there is a certain state, and the state keeps changing, right. So what I would like you to do is go and draw a state machine for the detect 1 1 problem. So this is the circuit that I gave, right. So I said the input is coming in from one side, and for detect 1 1 I said this is the circuit, right. What I would like you to do is go and draw the state table as well as the state draw the state table and the state diagram for this particular circuit. Once you get a handle of this, go and try doing it for the 0 1 1 problem also, the circuit that I gave for the 0 1 1 problem. Go and write the state table and the state diagram for it. So this will get you into the habit of drawing state tables, state diagrams and so on. And so once you do this, slowly we will start connecting how these state machines were built. For these problems the state machine was easy to build, but we are going to see more complicated examples in the next week, where coming up with such a circuit is not going to be easy. We need a more methodical and a structural very systematic way of approaching that problem. It cannot be something that we can think about and come up in a relatively quick manner. So we will see such problems where coming up with a circuit is not easy. We need a mechanism where we actually start with the state diagram and then come up with the tables and then come up with the circuit, rather than the other way around. So in the next week what we are going to see is, we are going to see what is called the synthesis problem. Right now I asked for analysis, given a state diagram or given a circuit, give me the state diagram and so on, right. So given a circuit like this, give me the state diagram is the analysis problem. The synthesis problem is the other way around. Given a state diagram, or give the state table and the circuit, or given a state table, draw the state diagram and give the circuit which realizes that and so on, that is called the synthesis problem, and we will see the synthesis problem in the next class. So what this does is, this brings me to the end of week 5 related to all the circuit videos. There is one more video that I am going to record, which is on Verilog. So in this week also we will do one more module of Verilog, and we will learn about what is called the always block. We have already seen the assign statement, we have seen how to instantiate, we know how to use primitives. In the next video on Verilog, we are going to see something called the always block. I will give you the motivation required for that, and that will be the final video for the week 5. So this video actually brings me to the end of circuit related material for week 5. So thank you, and I will see you in the next video before we close this week. Bye.